hoverboard. In this exercise we consider an hoverboard with a pendulum. Of course the pendulum in practice it is a human, and in this hoverboard which is purely two-dimensional, so we will not consider the three-dimensional aspect in this exercise. We have only one actuator, which is the motor which is between the wheel and the pendulum. And for the sensor we have an inertial unit. So the inertial unit is purely inertial sensor. So I mean it is only able to measure acceleration and rotation rate. So for the rotation rate we use a sensor which is a gyrometer. All is inside an IMU, so which is an inertial unit. For the actuator it corresponds to U, the input, and it is the torque between the wheel and the pendulum. So there is something which is important. It is the angle beta, which is the angle between the red and the blue, so between the board and the pendulum. So the human is able only to control this angle beta, so the human rider. So the human will only be able to tilt the board with respect to its own body, not with respect to the world frame. So it corresponds to this. So we have we do not have to confuse the angle theta, which corresponds to the pitch, and the human cannot control its pitch. It can only control the beta. So the other important angle is delta, which corresponds to the tilt angle, and which is the angle of the board with respect to the world frame. So it is the sum of theta plus beta. So as written here, delta is the sum of theta plus beta. Now we have in this exercise some coefficient such as the mass of the wheel, the radius of the wheel, and we can deduce the momentum of inertia Gm. For the rider we'll have the mass m, and we need to understand that the mass L as well as the size of the human is not known. We know that they are positive, but we have no idea, and it will complexify the problem. And since we don't know, we'll choose a model-free approach, so such as a PID controller. The first question is to find the state equation of the system. Okay, so we have this system, and we'll apply the Newton rules. So for this we have the board in red, and we have between the pendulum and here a reaction force, and I will call it R. And between the pendulum and the wheel we'll have this reaction force which will generate Rx and Ry. The degrees of freedom of my system will correspond to the angle of the pendulum and the angle S of the wheel. So S and theta will be the degrees of freedom, and the state will correspond to a vector x, and this vector x will contain S, Y, and their derivative. So S dot will be called V, and theta dot will be called omega. So x, the state vector, will have the form S theta S dot, so V and omega. And to have the state equation, I will need to have something like x dot equal f of x and u. nu is the torque between the wheel and the pendulum. Recall that the only thing I can control at the end is the coefficient beta. I write the Newton-Euler equation with respect to the translation of the first body, so the wheel, and the second body, the pendulum. So in translation and then in rotation. The mass and the dimensions such as rho, the radius of the wheel, will be involved in this equation. And here, take care, it's a vector equation where I and j correspond to these unit vectors. Okay, so A corresponds to the center of the wheel, C is one point of the wheel, and B is the center of gravity of the human or of the pendulum. So note that I need here B dot dot. So I write B here with respect to S to the degrees of freedom and I and J. I will compute the derivative with respect to T, and I will have an expression for B dot and B dot dot. So this one I can replace here. Okay. Then this equation, which is vector equation, I will decompose in two scalar equations. So this one. And as always, when I use the Newton-Euler method, the second derivative S dot dot and theta dot dot of the degrees of freedom, which are involved here and here occur. They are linear in the expression, so I can isolate them. And if I isolate them with respect to theta and S and their derivative, I will obtain this expression. And when I write this expression, so here it's U. When I write this expression, I will, for simplicity, make appear some coefficients, so mu1, mu2, and so on, which depend on the mass and the dimension of my system. So M, rho, L, and also the gravity G0, which is equal to 9.81 meter per second square. Okay. So since I have isolated S dot dot, and since S dot dot corresponds to V dot and theta dot dot correspond to omega dot, then I am able to write the derivative x dot here as a function of f and of x and u. Okay, so recall that x corresponds to s, theta, v, and omega. So I have this. Now from this, I should be able to program and to provide a simulation of this using, for instance, a Runge-Kutta method. So I will write a Python program where I have here my evolution function f of x and u, which correspond to this, and in this expression then correspond to this dominator, okay, occurring here and here, and mu1, mu2, and so on appears here. Note that all of them are positive. Here I draw my hoverboard, and here I use a Runge-Kutta method. So I put here beta equals 0, which means that the board is perpendicular to the body of the driver. And here also I put u equals 0, so it means that there is no control at all. If I do this, it corresponds to this program, where I do not show here, do not explain how I am able to draw the hoverboard. We'll see this immediately. So I have this program, I will run it, and I can see here my hoverboard, and we can see here the board in red, and this strange shape corresponds to the humans. So we understand that there is no control at all. Question number 2. So we recall that all sensors are inertial. I only have accelerometers and a gyrometer. But we'll assume that we are able to measure delta, the delta corresponding to the tilt, which is not exactly what is returned by the IMU. But we'll assume that at this step we have it. And omega will correspond to the derivative of delta and also to the rotation rate of the board. Recall that since beta corresponds is assumed to be constant, omega is the derivative of delta. So we have here a proportional and derivative control. Recall that we have no exteroceptive sensors such as a GPS or a camera. We do not have a pitch sensor to get the angle of the rider. All is inside the hoverboard. So now we have to prove that if the coefficient K1 and K2 satisfy this condition, so Kia both should be positive, but K1 should be large enough. And in this case, we have to show that we are able to stabilize the pitch angle theta. Okay, so recall that I had this state equation here. Okay, and from this I am able to extract this one and this one, and just to study the stability not with respect to the position, but only I'm just looking for the stability with respect to the angle or to the pitch. That's why I'm interested, because I will not be stable with respect to the position. The driver will have to do the job. So I extract this equation and this one, and I obtain this. And the controller I want to put is this one, and I will have to insert in this equation. Okay. If I do this, so I insert here, I will obtain this. Okay. So I will have theta dot and omega dot as a function phi, let's say, with respect to omega and theta, and from this I will be able, and the others are parameters, and from this I will study the stability. Another coefficient here is beta, and beta is assumed to be constant, so it's equal to 0 for the stability analysis. If I do this, I will consider to study the stability that theta is approximately equal to 0, so I will have a linear approximation. I will replace this by 0, because at first order it is equal to 0. This one will approximately be equal to 1 at first order, and if I do this, I will obtain at first order this equation. So from this to this, I have performed a linearization around theta approximately equal to 0 and omega approximately equal to 0. So it is a linear stability analysis around this point theta omega equals 0. I can put in a matrix form, so I will have to extract theta and omega which appear linearly, and if I do this, I obtain here evolution matrix A, and here the input, here I could write as a matrix B, And the eigenvalues of A, if they are negative, it means that my system is stable and I will converge to a constant value for theta. Okay. So for the study stability analysis, to compute the eigenvalues, I will compute the characteristic polynomial P of S, which is equal to the determinant of Si minus A, which corresponds to this quantity. I compute the determinant, and the characteristic polynomial becomes this with two coefficients, this coefficient and this coefficient. If I apply the Routh criterion, Routh-Hurwitz criterion, I obtain that this coefficient, these two coefficients, should be positive, and if I do this, I will have the stability. So this coefficient is stable if I have this, and this one is this one is positive if I have this, and this one is positive if I have that. So this is my stability condition for the parameters of my proportional and derivative controller to have the stability. Okay, so now I will be able to write my controller. My controller depends on the tilt angle theta and the rotation rate omega. I take two coefficients like this, one which is large and the other also, so I can tune them, and I check that I have the stability, so it is this condition, and if it is the case, so then I apply this input. Okay, so the controller which is given here, it is the one I have explained, and here I still use my Runge-Kutta method, and U is computed here, whereas before it was equal to 0. Here it is computed by the controller. As an input, I put theta plus beta, which corresponds to delta, the tilt, and for beta I put 0.3, so it means that the angle between the board and the driver is not equal to 0, so it means that I will probably accelerate. Okay. Recall that my inertial unit is not able to return me theta, so neither delta, so I will have later to compute them, to estimate them. But not now, it's a state feedback that I have here. Okay, so I run, and if I do this, I can see that indeed I have my acceleration, and there is a small angle between beta, between my body and the board. To implement the controller, we need only inertial measurements. So we are not allowed to use delta, the tilt angle. We are only allowed to use accelerometers and the gyrometer. So from this we need to build an observer which gives delta, an approximation of delta. So for this, I recall that I have a relation between the acceleration I measure, AM, and this measure is made in the sensor frame. So the sensor is the blue box we have here. So it collects me AM and also the rotation rate omega m. I look now only at AM. There is a relation between AM in the sensor frame and the one in the word frame. So in the word frame, I have the gravity G0, which corresponds to 9.A1, and the acceleration V dot in the direction of forward, to be positive. Okay, and I have between the two a rotation matrix which is given here, where to go from the word frame to the board frame, I will use the rotation matrix with an angle delta, or minus delta if you prefer. Okay, so I will use with this relation, and from this I first know it's important for me to find the acceleration v dot, which is one of my state variable. So v dot, to get v dot, I first notice that the norm of this vector and this vector should be the same, since here I have a rotation matrix. So since the norm of this one and this one are equal, I can write this relation. Okay. And I first need to find v dot. If I try to isolate v dot, I will have two solutions. So v dot equal to plus or minus this one, and delta, no, sigma, I don't know it. It can be plus or it can be minus, and it's a problem to find it, and I will show later how to find it. But let me first explain why we have two solutions. So if here I consider two situations where here my hoverboard decelerates, so v dot is on the left, is negative, and here v dot is positive. Okay. We observe that in both situations, the driver feel the gravity, so 9.a1 in the vertical direction, and feels also v dot. But it has no possibility, so here it accelerates, here it decelerates, but if he closes his eyes, he has no possibility to know if it decelerates or if it accelerates. It is only able to see that it is not totally vertical and not static, because what he feels is something which is an acceleration which is greater than g0, greater than 9.a1. So these two situations are similar from an inertial point of view, and here I draw the triangle in the body frame. So here I have 9.81, here the acceleration it measure, and here v dot, and I can see that what I measure is always greater than g0. I am able to find v dot, but which sign it is something which has to be estimated. So from this I will use the gyro. So from the gyro I am able to predict delta. Delta, since delta dot is equal to omega, and I am able to get it from the measurement, I measure it, I will have delta p is equal to delta p at time t minus dt plus my rotation multiplied by dt. So from this I am able to have an approximation of this. And from this I will have my relation between v dot, so the acceleration in my word frame and here in my body frame, and this one is the prediction, which is quite reliable and will allow me to have an approximation of v dot. So v dot is now given by, I take just the first line of this matrix equation, so I decompose into two scalar equations, but only the first one is interesting for me, and I obtain an approximation of v dot, which use my gyro somewhere and also the acceleration I measure. But this one is, I will try to only use this one to determine the sign, and sigma will be the sign of v dot, sigma will be the sign of v dot, and since I have an approximation of v dot given here, I will have here a quite reliable estimation of this sine I want. So from this, I have now a relation from what I measure and what I have in the world frame, and the angle between the two will give me an approximation of delta. So delta is the angle between the acceleration I measure and the acceleration I have in the world frame and in the body frame. So this angle I determine like this, taking the sine and the norm I have obtained before. I take this angle, and to get this angle, I will recall the formula between the angle of two vectors. I have to normalize them and to compute the determinant between the two vectors, and it gives me the angle. Okay. So let me show my controller. So I have my human here. From the inertial unit, I am able to get the acceleration in the board frame and the rotation rate. And from this, my controller is given here. Delta hat is the approximation of delta. To get delta hat, I use the angle between two vectors. The sine is determined using the gyro, as explained before, and I can now implement this controller. I take here my Python program where I compute delta hat with the observer. So the observer has to memorize an approximation of delta in order to perform the prediction. And the input of observer is only what I measure. So let me show the observer. It is given here. I first compute, I have a function to give me the angle between two vectors. I compute the prediction here for delta. Then I compute with the formula an approximation of v dot, and the angle between what I measure and what I'm supposed to have in the world frame give me an approximation of delta hat. Then my controller will use delta hat and Wm in order to compute my proportional and derivative control. So proportional derivative control given here as shown previously. Of course, I had to add an observation function which tells me that if I know u and beta and my state, it will return me am and wm. So this corresponds to one function inside the simulator. Of course, what I have to implement in practice, it is the controller and the observer. So let me run this function. If I do this, since I put the same situation as previously, I mean beta equal 0.3, if all is working well, I should accelerate. And I obtain exactly the same situation as the one I got previously without the observer.